Hi, welcome to my talk. My name is Tom, and you may know my work from any of these apps that I've worked on. And in particular for this audience, you may know r.swift, a tool for generating static resources for your Xcode project. This talk is about server-driven UI, and in particular about my experiences using and building it for Primephonic. Primephonic is a classical music streaming service. It has apps for Android, iPhone, iPad, a web player, a Sonos integration, and if you're familiar with Apple Music or Spotify, it is similar to those, but it also has additional features that are specific to classical music. We built Primephonic over the course of a couple of years, and we used server-driven UI from the very beginning. Let's look at a quick primer on what server-driven UI is. This screen is from the Primephonic app, and it shows a composer page. The screen is built up out of several components. At the top there's the artist header, there are 2 section headers, 3 detail buttons that link to other pages, and a text with a couple of paragraphs of text. The order of these components, as well as their contents, are all driven by the server. That means that if we want to change something, say we want to show some albums instead of the biography, we can make that change on the server, and we can release this without having to ever release any new versions of the clients. You may have heard about this ID before, and in fact it's not a new ID. Here are just a couple of examples of other approaches to the same concept. Airbnb has Lona, their server-driven UI framework. A couple of years ago, Spotify used the Hub framework. They have since made some significant changes. And 10 years ago, Apple had a presentation at WWDC about using server-side plists to configure your iOS application. And of course the web. It has always been server-driven. In '91 it was probably all static, the HTML, but since CGI, HTML has also been dynamically generated. Let's look at some differences between a traditional architecture and a server-driven UI. In a traditional architecture, you have a client that sends a request to a server. The server then responds with some JSON that the client has to render. In a server-driven UI, you have a client that sends a request to a server. The server then responds with some JSON that the client has to render. Okay, so to the untrained eye, these may look very similar, but the devil is in the details, and that's what this talk is about. Now, that was a bit of a global overview. Let's dive into the details. I want to talk about 5 different topics. How to build screens and components using this approach, how to do navigation, how to perform actions both locally and remote, how to do API design, and integrate it into the application, and finally, when is it not appropriate to use this approach, and maybe should you use something else. First off, let's build some components. We'll start small with a UI table view cell. This cell shows a single work by Beethoven, Piano Sonata number 14 in C sharp minor, opus 27 number 2, also known as the Moonlight Sonata. This looks simple, but of course there's a lot more to it than that. Looking at the domain model, we see there's a ton of more details. For each work there's a separate title, a number, a key, an alternative key, an opus number, a genre, a period, and some translations. Now, this domain model lives on the server. In some database there's a record with a lot of fields. Which of these fields do we send to the client? Do we send the whole object, or do we only send the data that is needed? And where does the decision live how to render this? Who decides that the key has to be in the first line and the opus number has to be in the second line? With a server-driven UI, this is all very simple. All these decisions are done on the server. This is all the data that is sent from the server to the clients. Just the title and the subtitle, because that's all that's needed in this design. Obviously, in a real-world app, there's a lot more details. Here are a couple of variations of that same screen or same component. In some cases we want to show the composer name next to the work, and in other cases we want to show the number of recordings of that work. Again, we can do this in a server-driven UI. The JSON has a bunch of extra fields, all of which are optional. So the client only shows a certain field if it is filled in, and the server has full control over what to fill in and when, and what to show when in the app. Here's a different example, a table view cell that shows an artwork. Again, all variations of are modeled in JSON. Here's a bunch of different fields, all of which are optional. What's interesting here is that the format of the JSON is very much influenced by the interaction design of the app. And in fact, when we were developing this app for the first time, the interaction designer, the backend engineer, and the app developer were all working together closely to discuss the different variations. And both the JSON model as well as the visual design were developed simultaneously. For a final component, let's look at something a bit more complex. This is a carousel. It lists the top composers in order of popularity. And we implemented this as another table view cell. But this one contains a UI collection view. Looking at the JSON for this, we see that the component is of type carousel, and there's an item type which references to the type of the items in the collection view. So we know for the collection view what cells to the queue. The items themselves are objects in the items array, and those again only contain the title and the image, because those are all that is needed to render this specific UI. Taking it all together, let's look again at the composer page. To render this page, we need to do one single API call. This API call returns all the data that is needed to render this whole screen at once. So going from the top, we have the type of this page, a component screen, a title, a header, an array of sections, and each section contains an array of components again. This whole page is implemented as a UI table view controller, and each component is a UI table view cell. The data that is needed to render that UI table view cell is all included in the original JSON. Okay, second topic, navigation. A topic that comes up quite a lot when talking about an app that uses data from a server is when do we fetch that data? How do we do navigation? So looking at these two screens, we see a screen that shows the list of composers, and when we tap on it, we want to show a single composer on a separate screen. But when do we do the API call? So naively, you might think of two approaches. One is you tap on a screen, you go to the second view controller, and that starts loading the data. Or two, you tap on the screen, it does the API call immediately, and then you have to wait for it to complete, and then you can go to the second screen. We didn't want to do either of these approaches because, one, we didn't want to have the web browser effect where you always go to a white page that then slowly loads data. And secondly, we didn't want to have navigation be slow. When you tap on something, you immediately want to see something happening. So the way we fixed this is to include the header for the second screen as part of the link in the first screen. So let's take a look at that. Here we have a screen recording, and I've enabled the network link conditioner to make the network connection seem slow. So I'll tap on the second item, Mozart. We go to the screen. It's now loading data, and here the data returns. Let's look at it again. I'll tap on Mozart. We immediately push the view controller. Here this view controller is doing the loading, and now it shows the data. So there are in fact three states that we have to deal with. The first screen that contains a link, which includes the header for the second screen. And when we tap that item, we immediately push the second view controller. That view controller is in a loading state, and it already shows the big header with a loading animation below. And finally, the third state is when the API call returns and we fade in all the data. Let's take a deeper look at JSON for the Mozart item in the Composer section. There's a title and an image, as we saw before, but there's also an action. That action already contains the type of the page that it will navigate to, so we know what view controller to load. It also contains the URL for the API to call and get back all the other data. And it has a header. The header is the exact same type of header that is used at the top of the second page. So it contains the image and a title and a subtitle. One interesting aspect here is that an image doesn't just contain a URL. It also contains a low-res URL. A low-res URL is used as a placeholder. If that image happens to be in the HTTP cache, it is shown while the bigger image is being downloaded. And what's interesting here is that we use the same low-res URL that is used in the previous page as the URL for the item in the carousel. So very often when we navigate to the second screen, the item is already in cache and we can show something as a placeholder. You may have seen my CocoaHeads talk from 2 years ago where I talked about the Rijksmuseum Art Viewer. There too we use the same approach where we use the low-res tiles as placeholders while downloading a high-resolution version of those tiles. So in practice, when tapping items in a carousel, we see a nice animation to a second view controller. When the top half of the view controller is already filled in with a nice background image and the lower half is being loaded still. If we look at this Composer screen itself, we see a list of works. And if we, for example, look at that first work, Eine kleine Nachtmusik, if we look at the JSON, we see an action, and this works very similar. It also has a header, but this is a different type of header. But all the this header doesn't include an image, but all the behavior is still the same. So if we look at the screen recording, we tap on the first item, we go to the second view controller, and the data loads in. In general, we are quite happy with this approach. It is a bit of work on the server side to be able to generate all the headers that are exactly the same as the header of the target page. But once you've done that, you get back this great benefit of having a very smooth navigation that doesn't show all these interruptions all the time. Moving on, let's talk about actions. The most obvious action you might expect from an app like this is playing music. So when we tap on the first item in this list, the mini player pops up and the music starts playing. How does this work with a server-driven UI? So the track is a type of component that contains all the information needed to render that component. It has a title, a subtitle and a duration, but it also has an action. This action is of type play. It contains a track metadata URL, which is the URL that when called returns a complete queue of all the music that needs to play in order. But similar to the header in navigation, it also contains a track, start track. And that object contains the information needed to immediately start playing music, so we don't have to wait for the metadata URL call to return. A different type of action that we call are actions that we call remote commands actions. These we can see in the menu in the top right. The JSON for this menu shows a list of actions where each action has a URL and a payload. That payload needs to be sent to that URL using an HTTP post. When we tap the first button here, Add Playlist to Favorites, we see a loader. That loader shows up while the API call is happening, and it blocks any interaction with the user interface. When the API call completes, we see Done, and the page behind it is being refreshed. Now that the page is refreshed, if we tap the menu again, we now see Remove Playlist from favorites. It's worth noting here that everything is very generic. In fact, when we first started implementing this feature on the backend, we implemented favoriting, having a database and all that, but we also implemented the user interface completely on the backend. So this is all driven by the backend. There is no client-side interaction needed. This feature was built and shipped completely from the backend, although later on we improved on it. Here we see a second type of response that a server can send. Instead of just showing a big done, the server can also ask for more information. For example, by showing a multiple choice list, or like in this case, asking for the user to type in some text. Here we see a part of the playlist creation and editing workflow. This whole flow is built and orchestrated completely on the server, without needing any code on the client's apps. Now, there are some things that can't be done on the server. Some things need deep client interaction. For example, the play action we saw before, but also sharing. Here we see a share button in the top right, and when we tap that, the system share sheet pops up. For this we need client-side logic. So what the server sends us is very basic. It just sends a title and a universal URL. The clients get to decide how to interpret this share object. In the case of the iPhone app, it shows a share sheet button in the navigation bar, and it uses the URL also for handoff between different Apple devices. And finally, in case you were wondering if we left in that ugly add to favorites in the menu, no, we also included a nice looking button that when you tap it becomes filled in. And in theory, the way we could have implemented this is you tap the button and completely in the background we do an API call and preemptively already make it the button be filled in. And if the API call returns with an error, then we have to unselect the button again and all that. We didn't quite get there yet in Primephonic, so it has a nice button, but when you tap it you still see the full screen loader. But at least the button looks nice already. Next, I want to discuss the specifics related to API design and how we integrated it into the app. As you can see, we use API versions, and after 2 years after release we already have 15 different versions of the API. But that's not a big problem. API versions are cheap. We introduce a new API version whenever we add a new component type that some existing client doesn't know about yet. So when a request comes in, the server looks at the version of the API and then decides how to respond to that. So if, for example, an app requests some page, but the app is an older version using an older API, and on that page is some fancy new carousel item, the server has to decide how to deal with that component. It can, for example, decide to fall back and show a boring old list there, or it can simply skip the whole component if it isn't that important that that old client sees that. As I said before, next to the GET requests, we also have POST requests, where the server or the client can send a body in a post, and that uses the same versioning mechanism. Again, this screen uses a UI table view controller. It uses a diffable data source to reload and animate the differences when reloading this screen when a remote command returns. We also use HTTP tags to ensure that if there's nothing changed on the server, then we don't need to do any animation. And the same goes for if the client cancels a request for some reason, we also don't animate. JSON parsing is all done using Swift's Codable. We create structs that exactly match the API types. If for some reason we need a different model, domain model, between the API types and the views, then we create a separate type for that. And we do manually map between the API types and the domain model. It should be noted that the server needs to support a bunch of different API versions, but the clients do not. Clients only ever need to implement one API version. So if we in some API version deprecate a specific component, then clients can just throw away that code. They never will receive that again from the server. One thing you may have noticed is the value or decoding error in the components array in the top struct. This is there to prevent against programmer error. In theory, the server should never send something back that a client doesn't know how to handle. In practice, programmers are humans too, and people make mistakes, so we have something for that. So the value or decoding enum is a safeguard. It's a generic enum that wraps a single value or an error. The decodable implementation tries to parse the input as the wrapped type, and if that decoding fails, then it returns an error, otherwise it returns the actual value. What that gives us in practice is that parsing doesn't stop when the JSON decoder encounters an error. So for example, if we're trying to parse a menu that has an array of buttons, if in the JSON one of the JSON has 4 objects and one of those 4 objects isn't actually a button or can't be parsed as a button, then parsing still continues after that one, and we still get back a menu struct. And if we look at it, we see 3 buttons in there and 1 decoding error. And the client can then decide what to do with that. In the case of Primephonic, what we mostly do is log the error and skip the item and still show the other 3 buttons. And in practice, that has already saved us a couple of times where someone made an error and it wasn't caught in testing. Finally, one interesting aspect of server-driven UI is that we can not just do an online experience when clicking through the app, but also build an offline experience using it. So when you're online, the app is in the background always downloading an offline version of of all your data, of all the albums that you've marked as being available offline. So that when you're offline, you can browse through all your offline albums and still see all the data that was originally generated on the server. That brings us to when is server-driven UI not appropriate? For the last year, I haven't worked on Primephonic, so I asked one of the current developers about his experiences with server-driven UI, and one of the examples he came up with was the offline experience. He said the single JSON response for the offline version became too large. While the initial development went very fast because of the reuse of existing components, for the offline page we needed to send the JSON for everything, not just the first page but all the subsequent pages as well, and it turned out that became too large. Some users had 20 megabytes big JSONs that needed to be synced all the time. So they switched back to a more traditional API. So in this case, server-driven UI maybe wasn't the correct approach after all. 2 other things in the app that aren't implemented using server-driven UI are the music player itself and the subscription flow. Both of these are deep OS integrations. So when you're playing music, the music player needs to update it now playing screen on your iPhone. You can use your AirPods as remote controls. You can control the app from your Apple Watch or from CarPlay. That's all very deeply integrated into iOS. And the same goes for the subscription flow that uses in-app purchases, and that's again deep and specific logic. And finally, here's an example of a completely different app as an example of when not to do server-driven UI. This is the Rijksmuseum app, another app I've worked on. And it allows you to walk tours in the Rijksmuseum and listen to audio descriptions. And it sends you from room to room, and it shows you the right audio descriptions for the artworks in that room. In this app, almost all the logic is done in the client. So the client downloads one big JSON file that includes all the tours, and then when you walk around and the app uses Bluetooth and beacons to figure out where you are, and all that is done in the client. So even though the data about which tours exists come from a server, this type of app, really server-driven UI, doesn't make any sense. And that is the end of my presentation. I hope you now have a better idea of what a server-driven UI is and how we've used it successfully in the Primephonic app. I've shown some implementation details and when maybe not to use it. Again, my name is Tom Lokhorst and I've recently quit my job. So I'm now available for something. If you want to start a startup to build a cool macOS app, contact me. If you know something else interesting, send me an email. Okay, for the people watching live, I'm now available for questions. You can ask questions in either the YouTube chat or in the CocoaHeads Slack channel. Thank you for watching.
Okay, I think I'm live now. Let's see, I have some questions already. As I said, you can send in questions in the YouTube chat, which I see here, and in the Slack channel. Jeroen has collected some questions. Let's see. Ezekiel asks, we are working on a server-driven UI framework here in Brazil. Cool. Which uses a backend for front-end to integrate your data API with server-driven UI. My question, do you guys use some kind of backend for front-end, or the original API was dedicated to server-driven UI? We built up everything from the ground up. So when we started, there was nothing. So we built up a whole classical music database and everything. So we built a backend for frontend, and we built it with the very idea of doing server-driven UI. So the database itself is generic, so we could use some other build some other API on top of that, but the only API that currently exists is the server-driven UI for the user interface. Roel asks, do you have a compatibility strategy that what would happen if the server suddenly returns an item type that the carousel component that is not supported in an older app version? Yes, and he added later that the question was already answered. So yes, we do have that value or error, value or decoding error type. So that helps. What we mostly try to do is, if we can, be forward compatible. So sometimes we have a carousel, and when we want to create a little variation of it, we add another field to it, so that the older apps just use the original version, and the newer apps get to do the little variation, so that we don't run into this issue. But if there is if we do have to make a backwards compatible breaking change, then well, the server side should handle it, and if it doesn't, the client will gracefully skip that item. Bruno asks, have you ever dealt with an app review not responding well to what could conceivably change the entire app from under their noses after approval? Did you anticipate and maybe prepare for this during development, even if it wasn't necessary? We did discuss it during development briefly, but we didn't really prepare anything for it. Partly because Apple had the exact same talk 10 years ago about how to use a plist to server-side drive your iOS app. And also, any app can always change something after it's been reviewed if there is a server behind there somewhere. So yes, with server-driven UI, we can completely change everything. But if we wanted to do that, we could do that in any way, using any sort of approach. You can always have a Boolean on the server somewhere that says, now show the other screen. So we didn't really expect Apple to care about this, and in practice, this was never something that came up during app review. Anton asks, will SwiftUI change the way you do server-driven UI? Yes and no. So when we built this, originally SwiftUI didn't exist. When SwiftUI came out, we looked at it and we said, wow, this is fantastic for this approach. As I said, for the past year, I haven't worked on Primephonic, so I don't know if they have started using it yet. But if I would still be working on it, I think it wouldn't fundamentally change anything, because our whole approach was use components that can be reused. And so we could just drop in SwiftUI for each of these components, and it wouldn't really change anything drastically. So not really. I think SwiftUI fits perfectly well. Tikitu asks, any thoughts about tight, fast feedback flows? For example, input validation that typically try to avoid talking to the server to keep super quick response times. Yes, so you saw the way we have these generic menus for adding favorites or changing playlists, and yeah, anything that has to bounce from the server back and forth doesn't really work. So this doesn't really work that nice. I mean, it works fine, but the user experience isn't very nice. So the best thing here, I think, is navigation. For navigation, this is perfect. As soon as you start doing non-local actions, so local actions also work, like start playing music. But as soon as you have to do non-local actions where you have to talk back to the server, then there's this delay and a spinner or a loader or something. So those aren't very nice. But in general, this app is a consumption app. So you browse through things and you play music. So that general flow works very well. If you have highly interactive things, it wouldn't work all that nice. So the things like creating and editing playlists, which isn't something you do very often. You won't be creating playlists very often. So we do use the remote commands there. But yeah, server-driven UI isn't the correct approach if you have tight local actions. Tikitu also asks, how do you establish a shared language of UI building blocks with designers so that new features can reliably be built using existing building blocks? So yeah, that's really, when we were developing it, we worked together very close with the designer and we built everything together. So the approach we had, or the way we worked actually, was very nice. The designer would create a sort of general idea of what he had in his mind, but then he sent over this half-finished piece of design to the developers, and when the developers got to implementing it, or one of the developers, specifically one of the clients, whoever was first, either Android or iPhone or the web, then the designer would sit next to that developer and talk through all the details. And typically, as I said, the designer and one of the app developers and the API developer were working together on a new feature. So do all things at the same time. Let's see, I have one more note, which is not a question. So if anyone has any further questions, ask them now. If not, I have to wait for the delay. Oh, here I see another question. Hong Yu Lu, how do you decouple the business logic from the iOS side to the backends? What is the backend looks like to generate these JSONs? I'm not sure if I understand the question. So it depends on how you interpret business logic. So what's interesting here in this app, more so than any other app that I've worked on, is that the app itself doesn't know very much about the domain So the app knows about the general concept of a component page, but in the domain, there are things like albums or composers and that sort of thing. But the app doesn't know about that domain at all. It only knows about components, and all that domain knowledge lives on the server. And the server, the backend for the front end, knows how to change what a composer is and how to change that into components. So that's interesting. And in general, I like working on domain things when I'm developing apps. So in this case, I worked a whole lot on the backend instead of the app, which I usually work on, because now all the fancy domain decisions have to be made on the backend instead of on the front end, other than things like playing music, which is all front end work. Let's see, that's the question I already saw. Yeah, so final question time. Be quick, because with the delay, I'm going to quit soon. So I don't see any more questions. In that case, thank you again very much for watching. Jeroen is typing, Yolanda is typing. So now, thank you. Okay, yes. Thanks so much for watching. As I said, I am available for something. So if you have any cool ideas about using Apple technologies to build something fancy, contact me. And thanks again for watching. Goodbye.